Okay, we will start. Okay, see, this part of the lecture also is continuing on ship trials and maneuvers. So I will start again from where we ended. You see, last class. So zigzag maneuver. Now we understand the maneuver. What we do, you turn the rudder, keep on swinging, and you measure that. What you measure here are these quantities. You see, this is what I should write down. Now, let me see these terms here all. This point will be called first execute, because that is the first time that you are executing the rudder. First time you are actually at this time, see, this is T here, right. This is the point of time where you have made the first execute of rudder. You have given the rudder angle to plus 20 degree. This point, this time is the time for second execute. Similarly here, third execute, etc. I mean, the 1, 2, 3 executes are the time when you have changed the rudder angle. Okay. Important thing that you find out is this, what is called overshoot yaw angle. You see, this is the how much it overshot. You see, it may overshoot. See, there can be a ship which can overshoot far this thing. Okay. Now come, so these things, this measure. So this is my first overshoot. Again, this is my first overshoot. This is my second overshoot. Like that, third overshoot. You understand? Obviously, I have given the rudder angle 20 degree. I would expect that the ship would reach 20 degree. No, sorry, rudder 20 and my set angle is 20 degree. So as soon as I set my my heading has reached 20 degree or that set angle, at that time I have actually swing it back. So it should have come back, immediately started to change, but it did not change. It started changing in the same direction for some more time and then came back. So how much more time it has, how much more angle it turned is my overshoot yaw angle. For the first execute, first one, second one, like that. Okay. Then comes the question of time. This is called, okay, I can also call this yaw overshoot. Now yaw, same thing. My yaw was at this point when I have my execute. See, at this point I change the rudder. Okay. So my ship would have started to come back on the other side, but it did not. It started going in the same direction for some more time. So this becomes my overshoot path width. How much it overshoots? You see, think of a canal. This is the canal size. It has come here. At that point, I have given a rudder back, so it should have come down. But instead of that, it kept on going some more time, distance wise. Okay. So always, overshoot is the maximum that it has reached from the time when the rudder has been reversed back, because from we expect that, I mean, in a car and all, rudder is reversed back, instantly the ship would turn on the other side. It does not happen for a ship. So it keeps on going in the same direction for some more time. That is what is called overshoot. So this is my first path with overshoot. Then also there are now question of times coming. This is the time. This time is known as reach. Okay. And then there are the time of period. It is actually time from this to this, one swing to other. It's become complicated, but I will just show it to you by description. This can be called period. You see, let me explain, not go into so much detail, because ultimately the overshoot angle is what actually is the IMO requirement. I will tell. Understand that basically what you are measuring is, you keep on turning the rudder this way, that way. You find out that the moment I change the rudder, after how long, number one, the ship's heading turns back and comes to 0, and how much more it kind of keeps overshooting in the same direction. This overshoot tells me how much it will keep overshooting, heading angle as well as path width, and what is the time taken. You know, you will find out that if you, it is something like, if you want to reduce this time, that means it should very fast turn, you will see that the overshoot is more. It is like somebody squeezed this graph from this, like you have a body and you are pushing it. So it is either normally you will find it's very fast it turns, or it goes like that. You can imagine that. See, if it respond very fast with radar, I mean the moment you give a radar, there is a force there, it would actually go down here, it will become want to turn, but it has already gone so much, it will go like that and then turn. So typically you will find that if radar is very effective, then overshoot goes up, the time comes down, because you are very fast it is turning. But then you don't want, see, in reality you may not want both together, because if overshoot is too much, it might hit the bank. So you always want a kind of balance, you see. That is why to say overshoot is, radar, huge radar I keep, it immediately turns, but it may turn, just hits and turn like that. You don't want it. So IMO requirement will actually come up with various kind of measures. Typically I will tell you again from this diagram, you probably should write down, reach will improve with radar effectiveness, means this time, how fast it will come back, how fast it turns, the quickness of turn obviously will be more if radar is more effective, and obviously will be less if the ship is very stable directionally, because if it is stable directionally, as in some book I read, it's like a dogmatic a mule, it doesn't want to change, it just wants to go along a straight line. So therefore it will take a long time to turn it back, that. So this reach will be, this will come down, it will get stretched this side, the full thing will get stretched this side, yeah, like you, as if you are holding and stretching this graph, if the ship is directionally stable and radar effectiveness is less. On the other hand, if the ship is directionally less stable and radar effectiveness is very high, then this gets squished back. So it will overshoot more but turn faster. This is what the general feeling is. I mean, I am not writing it down, but generally this is the case. And also there is a question of speed, obviously. Now you can expect that if it goes very fast, it overshoot will increase normally. If the speed is more, obviously it speeds up more, so it overshoots more, and reach etc. also will decrease. If speed is fast, it will go up, but it will reach faster because it is going fast. So there are all these kind of qualitative analysis, but what IMO tells is specifically that it must, some measures that I will mention later on. It says that this maneuver, the overshoot should not be more than that, or should not be less than that, etc., etc. It only talks of the first two. You can simulation, you can do it for infinite, it will become a steady state, it will just become like a sine curve. But they will tell about two. After all, no ship is going to zigzag 10 times, you see. Okay. So I want to go to this turning circle, because we have a time constraint. Okay, turning circle is the most interesting and detailed. Now turning circle maneuver, by the name, is the most simple one. All you do is that steady the ship, then give the rudder to some angle and sit quiet, do nothing. The ship will begin to turn on its own. That's all. And you measure what circle it took. Okay. So what you do is that you begin along a straight line, of course. You have here a ship coming. At that time, let us say you begin to give the rudder. Start rudder deflection from here. Okay, say from here, let us say this is my starting point. See, the ship is coming steadily. At some point, obviously, you begin to give the rudder deflection. Now, what would happen? The ship is basically going to go in a circle, but most ships will look like that. It will go some. This is very interesting, actually. First of all, I have to show the path, and then then it will begin to go like that maybe, and if you continue it will reach a steady state circle. So, the ship is going to go initially here, eventually it will come to a point here. This ship should be drawn by another graph. Like that. Okay. See, what will happen is that you are measuring the ship part. See, as you give a rudder, normally it turns out that there is the path that it will take is that the ship slightly swings on this side. You have given actually rudder in the, let us say, on the starboard side, that is this side. Okay, so the ship is supposed to turn on this side. See, you have given a rudder here, obviously this way. That is going to turn the ship this side, because you see, you can think of that as you can think this very simple way. Water is flowing past from this direction, so it pushes here. So the back side goes this side and comes like that. So it simply turns this side. Yeah, that is the interesting. Of course, I probably is an exaggeration. I will explain that. Many interesting thing happens. First of all, I will tell you that we can call this to be the various phases. Second phase and third. Okay. We can call some phase, small part here, to be then up to some point, maybe up to some point here, certain point here. Say here and then say I will explain what are these phases actually. Then before that can be called approach phase. See, what we are doing is, it's something like this. You are approaching here and there you are giving this angle. Okay. As you give the angle here, it takes some time, the ship basically turns like that. Now we have to, what you have done? You have simply taken the plot of that. In other words, you have simply measured the location of the ship and its heading angle instantaneously where it is located. Okay. It looks something like that, and it will of course begin to turn if you keep the rudder steady. Now, initially, as you give the let me see in the approach phase. Let me put this way. In approach phase, what you have got? You have got your velocities u dot acceleration v dot u and v are x and y, and r dot as well as r are all 0. Also v is 0. Okay. Because you are not accelerating, you don't have any v dot, you don't have any r dot, you don't have any r, you don't have a v. Because you see, all you have got is u. You only have u equal to constant. That's all you have got. Okay. Now there is a small part. Now what happens initially? This is what we have shown here. There is a small part, what is called first phase, where initially what happened, that the this ship begins to turn, but the velocity of, you have just given a rudder. Okay. So there, what happens? The rudder gives a force here. As the rudder gives a force here, you see there will be, if you give a rudder here, there is going to be a force here coming like that, moment here coming like that, moment here coming like that. Okay. See, now this is the interesting part. When you give it, I showed here, when you give a rudder here this way, what happened? That this is my CG of the ship. I will get a force this side. This force is going to be equal to this force plus this moment. okay, or rather with a color if you draw it, I am going to get a force here, rather I am going to get a force this side. This force is equivalent to as if there is a force through the CG and a turning moment. All right.
So the whole ship actually yaws.
Yeah, exactly. Initially it always yaws because there is a push here. So what happened, that part I will come this thing, why this swings here, what happened because of this force initially before it has have a chance to change its heading angle, this force is dominant initially, so this thing full thing has come slightly on this side. See this, you notice that I give the rudder angle here, immediately there is a force coming this side, so it first shifts slightly this side, then only it gets a turning angle. You see, before it could change the turning heading here, before it could that the ship can begin to turn here, this force has caused it to shift this side. That is why it has a slight overshoot on this side for quite some ship, because the rudder has caused a force on the other side. See, it is giving a force on this side and turning. This force is more, so it has gone slightly this side, then it is going to turn. That is why it has shifted. Okay, and we call a first phase to be one phase where as soon as you give a force, okay, force is mass into acceleration, you will end up getting some acceleration, but velocity may not have still developed, it is maybe very small. So there will be an initial phase, moment I give a rudder, there is a force I am giving. Moment I give a force, there must be an acceleration because mass into acceleration equal to force. Of course, you may say that will also give you velocity, but the velocity is still very small. That is why there is a phase where immediately there is an acceleration is rate of, remember that velocity may be small, but acceleration can be still very high because acceleration is rate of change of velocity. So I might have velocity 0 to velocity 0.02, velocity 0.03, but at a short time these changes are occurring. So I might have velocity small but the acceleration high. This is what happened initially for a small time. In other words, the velocity, it has not yet shifted, actually it is still more or less along this line. It has not yet shifted, but there is an acceleration. In fact, the graph will more be like that. So initially for a while it does not shift, okay. Then it begins to shift here. Then second phase is the most complex phase. In second phase you have everything there present. So you have got V not 0, R not 0, V dot not 0 and R dot not 0. So you have got everything present in second phase, okay. So second phase you have got all transit motion. Now it begins to turn. There will be some point, therefore it will now begin to turn steadily. So third phase, okay. Now what does it what is meant by steady phase? This is called a steady phase or final phase. So initially what happened, see, we will look at it this way, you are giving a force, there was a 0 force coming, suddenly you give a force. As soon as you give a force, it will first shift this side, force will introduce some motion, velocity and motion. Eventually, because the force is not changing with time, okay, you must have 0 acceleration because mass into acceleration is force. Therefore, if the force is now constant, after a while the force, you are not changing the force anymore, therefore acceleration must be 0. So in a steady phase you will have necessarily no acceleration, so you will have only your V not equal to 0, R not equal to 0, but V dot must be 0, R dot must be 0. See, when it reaches a steady phase, when it is going steadily like a ship, okay, along a straight line course, you must have ultimately no acceleration, because acceleration implies you are changing velocity continuously. See, having acceleration implies having forces, but here now the force has reached the balance, no more extra force on the system. Like a ship when it is moving steadily, please remember that the net force on the steadily moving ship is 0, T equal to R into whatever, and the resistance and propulsion just balances, the net X force is 0, T minus R is 0. If the T minus R was not 0, the ship would have been continuously accelerating. Newton's equation says that mass into acceleration is force. If my ship is moving at 10 meter per second, it is not changing, it is not having acceleration, which means there is no net X force.
So if the speed is becoming steady, always 10, that means there is no acceleration.
That is what is happening. So eventually this vessel will reach a steady turn, it will keep on turning steadily, which means it has got only velocities but no acceleration. see it has reached a velocity of say sway velocity of some meter per second and yaw velocity of some degree per second. It will keep on doing that. So, this is my final phase what we call. Okay. Now, there is a point where the ship is actually changing its heading to 90 degree, okay, from the start point. This distance is called advance. This distance is from this reference point. This is called advance. Okay. Let me actually get this 1 second diagrams little bit. Some people call it advance for 90 degree. Okay. And this distance is called transfer. Let me put it this way again. I am having this my x axis, this my y axis. Okay, along the direction. Let me call it x axis, y axis. The x distance from start point where the ship's heading has just changed 90 degree is called advance. X distance is always called advance, y distance is always called transfer. So, there is a point where the ship's heading has changed 90 degree because it has just now, you see you are going this side, it has just changed 90 degree. So, the x distance where this occurred you are going to call it advance, and y distance where it occurred from the original line you call it transfer. Same thing would of course occur to 180 degree. This is where it has changed to 180 degree, just opposite 180 degree. Then you will call obviously here to here transfer at 180 degree, and this is actually called, some people call it tactical diameter, you see, or steady, this is called, some people call tactical diameter. So, this is actually I will tell you this distance, see distance where heading has changed 180 degree, where it has changed 90 degrees transfer, that is this line, where it has changed 180 degree it is also transferred to 180 degree, which is called tactical diameter for a ship. Okay. And this, of course when it has reached a steady turning radius, then you have got the steady turning diameter. So, this distance, the diameter that is reached, this is my steady turning radius, you can call R steady turning radius. And this distance is maximum transfer. I will tell you, you see, because we have to squeeze time, where I'm
Maximum transfer and 180 transfer is almost same.
no, almost, but not exactly same. I will explain to you that later on that this heading angle is absolutely necessary for a ship to turn. You cannot have a ship turning in this way, like this. It has to turn this way. It is a must, because if you don't have, then the ship doesn't turn. So, there is a so called beta angle, that is this angle, there is drift angle. Speed vector is here, the heading is there. This is my drift angle, okay, beta drift angle. Drift angle has to be non-zero for a turn. If it is not non-zero, it cannot turn. It is not like a car, it can turn. It has to turn like a plane or something like like this. There has to be a heading angle.
The same way, the first part of the
Here it has not yet changed. Here, there is a heading angle.
angle will be little different.
Yeah, little different. Actually, I didn't show it here because heading angle is,
Inward.
you see, yeah, it will be inward. It will be always inward here. Yeah, actually, see, initially heading angle has not yet developed, like because R0, V0. Eventually, it will begin to develop heading angle, and ultimately in the steady phase, it will have a steady heading angle. In fact, heading angle is connected to V. You will find out that heading angle is actually V, beta equal to V. We will find it out. But anyhow, first the measurements, then this other part. You see, what is happening is that in the first phase, as you know, in the approach phase, forget it, first phase we have got just the accelerations have got set up, velocities have not yet set up, the ship has swung here because Yaw forces pushed it up here, heading angle has not yet changed. Okay. Now second phase, you will have everything there, and now the heading angle slightly begins to change, everything is there. So there is a continuous change of heading angle up to this point, and there will be some point when now heading angle has become fixed, the accelerations have become fixed, the ship is just turning steadily. If you leave your rudder and you go to sleep, it will keep on turning on a circle. Okay, and you are of course not changing the engine. Remember, of course, one thing is that one also measure the speeds, because the approach speed u has changed here because of the angle here. There is an extra x force that comes, so speed actually also changes, that the forward speed, that u also changes. But of course it will change, and eventually that also will reach a steady state. All of them will reach a steady state, but initially there is a reduction of that. See, when you give a rudder, you are giving an extra drag force also. So obviously the speed also changes, because you are not changing the engine setting. Engine setting is fixed. Now the distances along x axis is called advance and y axis is called transfer. So there are 2 points to note. One is where the heading has changed 90 degree, one where the heading has changed 180 degree. So at 90 degree heading angle, you have transfer to 90 degree, and advance to 90 degree. 180 degree heading angle you have got, you don't call advance anymore, because advance is lower. See, here you need to know the advance, because you need to know how much it has gone ahead before it turned. See, you want to know, no? Suppose there is a wall there, you are turning, you need to know whether it can actually turn before hitting the wall. So you need to know the advance. See, suppose there is a something there, you have to turn, you give an execute here, you need to know how much it has gone maximum. So the maximum is not measured actually, instead of that you measure this 90 degree heading angle normally. Similarly here, when it changes to 180 degree, you see how much it has shifted that side. Essentially you actually take this radius, ultimately we will see the radius, but these are the measures you actually have. So you have the 2 point measurement, 90 degree heading and 180 degree heading angle. So x and y distance of that, y distance of that. You measure also the speed here, you measure of course this drift angle, and finally you measure the steady turning radius. That is the most important thing that you measure. And you of course also have record of time, at what t this occurred, what time it occurred, the time for heading of 90 degree change, time for heading of 180 degree change, and if you want time for 270 and all, but normally people don't go beyond that, because this completes a U-turn. After that you don't want to keep turning actually in a real atmosphere. There is no practical interest beyond that point. So you actually do that only to find out the steady turning radius, but then you end the test. No, you don't turn, like there is no point. You might at best turn up to this and then go this side. But this is done because you want to know the steady. See, although you do only this much, you want to know the radius. That to know the radius you have to make a full turn for the trial purpose. In real maneuver you may not do it, you see. So having done that, we will just do a quick plot of this the values of various things in first and second phase. See, we have got rudder angle here, okay. You have got V air and drift angle. I'll tell you that V and drift angle are actually same with a negative sign. This is small v. Then we have got V dot and R dot. These are all measured. Huh? Now rudder is given like this, and rudder is kept fixed. This is my rudder. This is time. Rudder is taken and kept fixed. Okay. What happened to this V dot R dot? What would happen is that acceleration initially will get set, eventually will come down and eventually will go to 0. Similarly R also is going to be something like that. Say it is actually plotted that way, so I am going to plot this way. R may sometimes come like that, and whatever it will also go to 0. This is my R dot. Whatever, it will basically have some value and go to 0. Now maybe you can use other color. This is V and beta, and we have got this So, this is this small part is first phase. Okay. What I mean is that the typical behavior will go like that. As you turn the rudder initially, there is a immediately it will keep acceleration v dot r dot, but the increase of v and r, that is velocities, are very less. So, there is a small time when we can call it first phase. It is not very important really, first phase, second phase, etc. Final third phase is the most important one. Then you see, then everything will be present non-zero, but eventually this acceleration will go down to 0. And velocities and v and r will become constant. Obviously, acceleration 0 means v and r constant, because dr by dt is r dot, dv by dt is r, this thing. So, when v and r has become steady, fixed, does not change with time, v dot and r dot becomes 0. So, at this point onwards you have got a steady turning rate. In fact, this is what you are measuring. If you remember, for a given rudder angle, we wait in this earlier maneuvers till r has reached a steady state. Basically, when r has reached this value, I can say now that if I give rudder of so much angle, my steady r is so much. That is what we have done earlier. If you recall, earlier we have actually turned the rudder, waited as long as we want till r has become a fixed number, which is this one, then it does not change anymore. Then I have changed the rudder again. That is how I have proceeded. Okay. So, it becomes like this. Now, what happened? From this we can of course analyze the ship's behavior, and we will go to a little bit of maths, very less amount of maths to tell you something regarding this phase. You see, this phase is most important, because this phase I have got v equal not 0, beta not 0, but v dot is 0 and beta, r not 0 and r dot equal to 0. So, I can go to my equation of motion and try to find out, because it will be very simple, since the equation of motion will have only v and r. So, there will be two equations. If you recall, my earlier equation has something v plus something v dot plus something r plus something r dot equal to something. But here I will have simply something v plus something r is something, something v plus something r is something. So, I can solve for v and r very simply. I will not solve it, but I want to show you the solution part, this thing. See, if you look back our equation of motion, okay, for it will reduce to I will just write it from here. See, let us not get threatened with this equation so much. I have a reason for writing this equation. Maybe I will not bother about this. The reason for writing this equation is that, see here, see my earlier equation, if you went back, you will find that there was something into v plus something into v dot plus something r plus something r dot equal to this. So, I have got 4 things, v dot r dot v dot r dot, and I had a more complicated solution. But this is very simple. This is something like ax plus by equal to c, a1x plus b1y equal to c1, a2x plus b2y equal to c2. That is all. So, I have got 2 by 2, like matrix, and I can, without any thinking, I can solve for this v and r. Okay. I can just like that solve for this v and r, which I will show you without going to the solution. I will show you. But before that, I want to tell you that supposing there is a ship here, you see, this heading angle part. Now, I have got here the ship normally going like this. This is my x axis. Okay. This is my v. This is my heading angle beta. Now, you see, this is my x axis, this is my y axis. Okay. Now, you see, small v equal to, supposed to be your cos beta. No, sorry, not cos beta, sin beta. with minus sign. You see, let me explain that to you. What happening is that this is my small v here. Small v is supposed to be in this direction, that 90 degree to to this. No, this is my u, this is my v. So actually in this case what happened, my v happens to be, if my beta is positive, okay, v happens to be big V into sin beta. See, my V is big V into sin beta with minus sign. Why minus? Because when beta is positive, V is negative. Basically, I don't want to go to the detailed part of it, but my definition of V dash equal to V by V. Therefore, it becomes minus sin beta. This is become equal to beta because beta is small. So what happened is that drift angle is nothing but non-dimensional wave velocity, because this diagram may not have been clear, but if this is my v axis, okay. So if this is my v axis, this is my u here, my small v is this one, because you can draw a try like rectangle. If this is my v here, okay, then this is my small v, this is my u, the two resolutions. This small v is nothing but v into sin beta. So V is sin beta, but V is negative for positive beta, therefore it is like this, therefore V dash is minus beta. Why I am saying is that when I make this, so there is only reason without mathematics, when I make it non-dimensional, when I like it all this way, like make it all non-dimensional, this non-dimensional, actually this u will go away because this will become 1, this will become 1, I make it non-dimensional. This is of course not necessary, this delta part. Then what happened, V dash become equal to beta. So what happened, that we have an equation therefore in terms of beta and r rather than V and r. You see, I have got an equation now, something into beta plus something into r dash equal to something, something into beta plus something into r dash equal to something, because this is nothing but V dash. That is all I want to tell you. Now if you do that, you will find out that now also there is one more thing there, r dash we can show is equal to L by R. If L is the length of the shape, I am not proving that, but in fact we can also prove that. See, R dash by definition is equal to psi dot dash, which is equal to R into L by V. That was my, if you look back the non-dimensionalization, it was like this. I had R dash defined as R L by V. Okay. Now that means R equal to R dash V by L. Okay. Now R by definition is V by R. The radius, steady turning radius into by definition V equal to R into R. See, this is I don't know how to say that, actually it is something like V equal to omega into R from this formula. You see, omega equal to V by, if something is moving at a there is a linear velocity is V and angular velocity is supposed to be omega, then omega R equal to V. That is the formula. You see, if the rotational velocity is omega, radius is R, then omega into R equal to V. So here my rotational velocity is R, radius is R, so R is V by R. This is only very simple algebra. All I want to tell you is that if you use this kind of thing, you will find out that R dash, which is by definition R L by V, R L by V will turn out to be L by R. In other words, basically this R term comes in. This is non-dimensional yaw velocity is L by R. L is the length of the ship, R is turning radius. If it is confusing to you right now, my purpose of this slide was to tell you is that as V dash can be written in terms of beta, similarly R dash without derivation, let me tell you, R dash can be written in terms of capital R, which is the steady turning radius. Okay, because R dash is non-dimensional heading yaw velocity, which is velocity into L by V. Because V and R are connected, these two are connected to each other through the radius R, therefore R dash can be related to capital R. That is what all I am trying to tell, because you see the direct velocity, tangential velocity and the rotational velocity are connected by the radius. Tangential velocity is rotational velocity into the radius, right. So, all that I want to tell you is that V dash is connected to beta and R dash is connected to R. So, I can write this now something into beta plus something into R, something into beta plus something into R is something, so that I can solve for beta and R. You know, it's a 2 equation, 2 unknowns, I can solve for what is beta, what is R. That is as simple as that, there is nothing complicated. And if you do that, you see, you will find out that R will become something like minus L by delta into, there is a term there, all this term will come in y dash v etc. like that will come, and v dash which is minus beta will come to minus delta into something, it will come like that. I am not proving that if you put that, but what I am trying to say is that you will basically find out that in one of these, this bottom part, in fact let me see that from here. Forget it. We will find out that here there will be a part, I think that this bottom part and this bottom part, we will find out that one of them are related to the stability criteria. You will find out that if there is a stability there, this positive, then only this relation will hold. Never mind this part. What is important is that R becomes minus L by delta into some term. Let us look at this carefully and see what physically the meaning is. See, this part is all a function of non-dimensional derivative for the hull. So, there is a constant for a particular hull. Okay. Similarly, this is a constant for a particular hull. Okay, because this term if you write down, it will be y dash v, m dash g, whatever. Okay, this is a for a hull. What does it show? That R therefore varies with respect to L and R varies with respect to 1 by delta, which means number 1, that longer the shape, larger the radius of gyration. That is why we actually have this as a criteria. You know, you will find out that the IMO criteria is connected to R by L, not R. Also, R is inversely proportional to delta, which means more the rudder angle, smaller the radius of turn. V dash equal to B minus beta is, if you see this part, V dash and delta are related. More delta, more V dash means more drift angle. And in fact, without proving, I can tell you that from this sign minus and plus, also one can tell you that the ship is always, if you give a port rudder, it is going to turn on the other side. This basically means that if the ship is turning like that, if it is turning fast, it is going to have a very large angle. The V is like that, this beta angle. And if you give rudder is very strong, then it will have a very large this angle and turn. If rudder effectiveness is smaller, then it will be like turning with a smaller angle. Sorry. Or maybe another one I will draw. This is very interesting from the observation point of view. You see that, let us see from this side turning. This is better maybe for me to draw also. V here, ship is going to turn very fast. Large theta and V dash, okay. Large rudder, or you can say large rudder angle. Small V dash B if the rudder is turned small. That makes sense. You see, if you have to, and then of course, and small r. This small beta V dash, large r. This large or more effective rudder. Large delta r or more effective rudder, small delta or less effective rudder. So, if the rudder is very effective, it will turn fast, smaller radius, but of course larger drift angle, and obviously it will slow down more because there is a large angle you are giving. So, this is what the typical characteristic is, and in fact the IMO requirement stipulates something connected to the turning ability, etc., etc. Okay, this is essentially the part we have to talk about IMO. So, I have to sort of let me see if there is time there, otherwise next class we will do. This is very interesting, interesting from many point of view, because first of all it tells you that, you see, you cannot have, if you look back at this equation, you cannot have, in this relation we will find out, any r. In fact, we can prove that if you take r and delta, if there is no beta. Beta is an essential part for turning. You have to have a beta for turn, in which means you cannot have a ship turning which is actually following the same line. It cannot go like that, it simply cannot go like that, rather it has to have a drift angle. If it did not have a drift angle, you can do that, provided as you do in a maneuver test, because you are holding by something else and turning it. On its own, by radar it cannot turn if it does not have a drift angle, which is not like a car. That means when it is turning, its x axis and the direction of velocity is not same. You see the point, which is not same in the case of many car or something. When you are turning, you do that and the car follows that line. Here it is not so. In fact, aircraft also it is not so. It has to be, when it comes down plane, sometimes it comes down like that. So there is an angle here, velocity is this side, but the x axis, like the plane is, I cannot draw the plane really, I don't know, okay, let me see. But velocity is coming down like that, and a plane is coming down slowly like that, but it has an angle. See, it comes down like this, for example. Okay, this is I mean, interesting observation. There is one thing that maybe I have time to do. That's even more interesting, is hill during turn. This part, let us quickly, very elementary one I am going to tell here. Say here a ship here, okay. So you have got here radar here. Draw all this stuff. This has become like a tanker with a big thing, radar here. This is a radar, The center of gravity, say G, is here. It is turning one side, okay. Now as it turns, as you know, okay, it's very quick time there. As you know, as it turns, you have to have here a centrifugal force, and this force is delta V square. Delta is actually weight. In fact, I like to write weight, or mv square by G. In fact, okay, mv square by R. M being the mass of it. Okay, this is a sort of this thing, and you have here a radar force Fr, because it is turning this side direction, and a reaction for Fh. Okay. See, as it turns, radar gives a force here. See, this is now here. Basically, we are looking at this way. The ship is turning this direction. In fact, I don't think I have time. This thing. So you have given a radar. So there is a radar force here. Okay. This is my Fr. As it turns here, there is a centrifugal force, centrifugal or petal, I have to see. And there is a reaction force to the hull. Now, I think I am going to not have time for this, but we'll start from here. But what happened, interestingly, that interplay of this force will cause the ship to actually heel, and it turns out that the ship heels on the outward direction, you see, and which we will discuss. In fact, there can be a problem on that how much it will heel during steady turning. And the most interesting part is that when you are turning outward direction, and we will show later on that if then you suddenly bring the radar to 0 degree, you are in a very much danger to actually suddenly increase the heel and even capsize. So the ship is going to heel on this side as you are turning. Some captain decides to bring the radar to 0 at that time. So all of a sudden, then it will actually at an instant it can actually turn more. This we will discuss how much it turns and why it turns little more. So it is dangerous for the navigation person. You should not like quickly turn the rudder to 0, you should do it slowly. Okay, so I will end it here. Unfortunately, this time, this class time ran out, but otherwise I would have wanted to finish it. But we will discuss that next class, this as well as the IMR requirement, and then follow with a rudder. Thank you.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own. through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs.
আকাশানি হার মেনেছে লোকে মোরা যাবো তাই দেশের তারে খাচ্ছি সবে আমাদের গর্ব ভাই যোগ কর্ম সুকৌশলম যোগ কর্ম সুকৌশলম একে সিদ্ধে বর্ণ যোগ কর্ম সুকৌশলম आदर्शाय आदर्शाय प्राणदास्मह्यम् योग कर्म सुकौशलम् योग कर्म सुकौशलम् योग कर्म सुकौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.